Today I've prepared a talk about some important properties to calculate using molecular dynamics simulations. Originally, Professor Luis Gustavo was going to deliver this talk, but unfortunately he could not be here with us today. So myself and Tuanan are going to share his the overview of what his planned talk was going to be. So in my talk, I'll be briefly covering some thermodynamic, structural, and mechanical properties. So this is an outline of our presentation today. First, I'm going to talk a little bit about what is the output of the molecular dynamics calculation. So basically, up until now, we've talked a little bit about how the force fields work, how we should perform convergence calculations, all the steps necessary to reach calculations that are statistically coherent. So now we're going to turn these output from the various packages, or if you do your own implementation, into properties, into fundamental knowledge. So basically thermodynamic properties, structural properties, and mechanical properties. So first, let's talk a little bit about what is the output of molecular dynamic simulations. If you look back at the earlier talks, you see that we can divide in the modern packages of molecular dynamics the output in two forms. The first, which is the more authentic form, would be the simulation trajectory. That is the evolution over time of how your system is changing. So you have, for example, atom positions, atom velocities, forces, atom species, all over time. So all the per atom relevant information is included in the trajectory. So this trajectory allows us to visualize how the system progresses over time. On the other hand, we can have the simulation data, which basically, this is something that is more common in the more modern packages, where we can have, for example, lumps already computing some of the properties we're going to see here automatically, which are essentially intensive and extensive properties of the system as a whole, things such as pressure, temperature, and energy. So here I have an example from my previous talk about the LAMP's output. And you can see here in this box, you have the trajectory. That means you can have some examples of what LAMPS calls the dump. And you can see here different types of trajectories, which can include different types of information. And here you have what is called a thermostyle, where you can output simulation parameters and also quantities that are related to the system as a whole, such as temperature, pressure, and other aspects, energy, and so on. So this is basically division of what, for example, LAMPS treats this output. So now I'm going to talk briefly about some thermodynamic properties that LAMPS can produce as output, and other packages, of course. So the temperature basically uses this statistical mechanical relation in order to compute the average temperature for the simulation. And using what Professor Kalinin showed, if you have the average of an ensemble, you can estimate that you have the average temperature for a given time. So basically, this is the relation used to compute temperature. So you have the masses of the atoms and the velocities in order to compute temperature. In order to compute pressure, you can use a similar statistical mechanics relationship, and you can employ also, in this case, the potential, the forces employed on the atoms, their distances, and the temperature, number of atoms, and other constants. The energy of the simulation, the internal energy of the simulation, can be comprised of the kinetic energy and the internal energy. The kinetic energy is closely related to the temperature of the system, as we saw before. So you can relate it directly to the temperature, as well as the momentum of the sum of the momentum of the atoms. While the potential energy is basically what you define. So you using your internal potential, your interatomic potential, be it a pair potential or a many body potential, you can describe your potential energy as a sum of all the terms, the different aspects for different pairs or triplets or etc. This is a simple example to show how to calculate density. For example, in this case, you have basically the number of atoms, the mass, number of atoms, or over what? A volume. This can be different in several ensembles, different ensembles. For example, we have an NPT ensemble where we have a density that will change over time, because in this example, the volume of your simulation box will change. So in this case, you can your density will be an output of your simulation. If you have, for example, an NVE or NVT ensemble, your density will not change over time because the volume and the number of atoms will not change over time. The free energy can be also calculated, but the absolute value is only possible for systems with very few degrees of freedom. So in practice, and this is a common occurrence when it comes to energy in molecular dynamics simulations, you have to calculate free energy differences. So enthalpy, internal energy, and entropy differences can be calculated using thermodynamic relationships. And besides that, we can also employ some other approaches, such as the free energy perturbation and single-step perturbation, when you can randomly insert an atom, for example, in the system and evaluate what is the displacement of energy in this case. So this is an overview of how overall thermodynamic properties can be predicted. So overall, when you have simulations, the actual values, since you're dealing with a numerical method, after all, the numerical values are not physical. They are not absolute. So what we need to do is always use relative terms to compare systems. So you compare the potential energy of different configurations per unit species or per atom to compare different configurations. And of course, what was said before, stressed here once again, that it's always important to properly sample your system, so you can avoid the initial steps of the simulation when you can have more variability, for example, here. So now I'm going to talk a little bit about structural properties. So these properties, most of them, they, with the exception of the mean square displacement, they are properties that you can evaluate for other types of calculations. So they don't depend on the on being molecular dynamics simulations, for you to study. So you can use, for example, some of these methods to extract information from your DFT output, for example. So the first method I want to approach is the radial distribution function. What it does, it basically calculates the probability for a given pair distance for you to find another atom for such a distance. So here we have an example of what a normal RDF curve looks like. And we can see here that as you progress through different phases of materials, from solid to liquid to gas, your RDF tends to lose definition. So in this case, this blue line here, you can see very clear definitions for first neighbors, second neighbors, etc. But when you go toward liquid and then gas, you have a much more random distribution. So you don't have as much definition in specific intervals. So this radial distribution function can be used both inside the package. For example, LAMMPS has a compute RDF function, or you can take your trajectory atoms, for example, and use a post-processing software such as Ovito, where we can see the window from Ovito here, and you can compute not only the complete RDF, also but the partial RDFs, when you can, for example, check only for copper-copper distance or copper zirconium distance, and so on. So this is an overview basically of what radial distribution function is. The mean square displacement basically allows us to estimate how much a given particle of the system travels. So we can see here, For example, this is a sampling of an atom, and you can see that they can occupy different positions over the system. So this is an essential property. So when you want to estimate, for example, diffusion, self-diffusion, or diffusion of one species into another. So it's a very important property. I believe maybe Tonão is going to talk a little bit more about this in his talk. So now I'm going to talk a little bit about some other tools that can help you understand or better identify your configurations, be it from molecular dynamics or from density function theory calculations. So first, I'm going to talk a little bit about how to calculate, for example, the void fraction of your simulation. If you have a porous nanomaterial, sometimes it's of interest to know what is the void fraction for the system. In this case, the method I commonly employ is a Monte Carlo based method. So in this case, you take your configuration or your series of configurations, and you randomly insert different probes with different radius. So when you see and you calculate the distance from this probe to the other atoms. So as you can see here, if you have hits, you exclude your probe and move on to the next one. So you can have, for example, in this case, a picture of what your system looks like. And you can use this to calculate what is the volume of the empty volume and the volume of your atom, which in the case is this spheroid here. So this information can be useful when you want to compare different materials, compare your configurations to the literature, for example, as is the next topic, which is a surface area. So how do you estimate the surface area of molecules or porous structures and so on? Once again, I employ a method that's based on Monte Carlo, but in this case, it's a little bit more sophisticated. So for each atom in your system, what you do is you create a number of probes that are distributed evenly along a sphere of radius that you define, for example, and you start to add probes along this sphere. And you can see here some probes will be accepted as they don't overlap over other atoms, and some will be rejected. And when you consider this, and you do this for all the atoms in your system, you can end up with something that looks like this. So this is basically visualizations of what this surface area method does. And by doing so, we can estimate the surface area of the overall molecule, for example, which will be, of course, dependent on, for example, the radius of the probe you use. And this is interesting because this allows us to, for example, use different probe sizes to obtain different values of surface area. But you may ask, what is the true value? And the question is, there is none. So when you are doing an approximation, one commonly used value for probe size, for example, is 3.72 angstrom, because that is the diameter size of nitrogen gas, which is commonly used to assess the surface area of several different, from molecules to porous nanostructures, and so on. So you can compare your results with different references by changing this pore size. So you can estimate the value of the surface area and be able to compare it to different references depending on the parameters you employ on this specific calculation. And when you modify this criteria, yes?
Okay. When you put this sphere, where put the origin of this sphere, is on the position of the atom, or is it a random position?
Basically, when you put the probe around, basically, it's, for example, say this atom. Yeah. You put in a sphere of the radius of the atom. So you take, for example, the van der Waals radius. You increase it by the radius of the probe. For example, you want to use 3.72, so you take half that, half the van der Waals radius, and in using an algorithm, you can put it over the surface of this sphere that has the radius of the probe plus the van der Waals radius, and you put it in a random position. So for each atom, for example, you can place up to 10,000 probes per atom. So you can get a very distinct, here it's a little bit difficult to see, a very distinct vision of how much each atom contributes to the surface of the entire system, for example.
Why do you use a random position near the atom and not the region of the atom? Because you have a position there to the sphere. The region of the sphere in the same position of the atom. It does not work.
Well, you use it as a center the position of the atom. So you place a sphere around the origin of each atom. So as I was saying before, we can modify this criteria to study more specific systems. So let's say, for example, that you're studying the adsorption of molecules or clusters on other systems, which is the case here. You are studying the adsorption of gold clusters on TMDs. You can use the similar criteria to estimate, for example, what is the contact area between your cluster and your nanoflake. And this allows you to compare, for example, a great number of configurations and have a feasible number that can be correlated, for example, with the adsorption energy or the relative energy of the structure as a whole, for example. So you can modify this idea presented here to better suit what you're trying to study, for example. Beyond that, we can also determine from given configurations what is called the pore size distribution, which is essential for characterization of porous materials. So for example here, this method is similar to, yes? Yes. Well, the idea is that once I said, like I said before, the value of the surface area depends on the probe size and depends on the, for example, you have the fixed value for the van der Waals radius of the atoms in question, but it depends on the pore size. However, if you use the same pore size for all the configurations you're studying, you have the same basis for comparison. Besides that, what you can use is to increase the density of the probing, so you can have more probes per atom in order to get a more refined results. If you use few probes per atom, you have a very varied result. But if you use a lot of probes per atom, you can get something more refined, for example. So, like I was saying before, and this method is similar to Monte Carlo, but it also employs some optimization algorithms. So you place, for example, a probe in a given point in a porous nanostructure, and you advance it using an optimization algorithm until the point where you can no longer move and increase the size of your probe. So in this case, you have several steps, but you end up here and you can move no further. So this is basically one point in a curve such as this one, which is the pore size distribution for these materials here. So in this case, we can see the information we can get from here is that what are the most prominent pores that you can see in these materials, and how are they more common related to others, and how well defined are they. So if you have a great number of different pores from different types, you can get peaks that are less defined, and on the other hand, you can get peaks that are much more refined when you have pores that are very common and very well defined, for example. Okay, so basically that was an overview of these structural properties. Now I'm going to talk a little bit about mechanical properties, how you can use molecular dynamics to estimate mechanical behavior on systems. So one of the basic tests that I've shown a little bit on the other talks is the tensile strain test, which consists of imposing a fixed strain rate on one or more of the axes of your system and up until the point of fracture, while you evaluate the stress on the structure along the way. So here we have a clip that shows the boundaries of the box clearly being strained up until the point of fracture. So this is a very common test, and you can use it, for example, for many different types of systems. And we also have the indentation tests, which consist of pushing an artificial indentator through a 2D or 3D material in order to compute the force that is necessary to rupture the material. This is commonly used for 2D materials because it's widely employed and allows you to have a experimental reference, because this type of test is commonly used experimentally, like Professor André talked about yesterday. And it has another advantage because in this case, when you compare, for example, different structures, the different types of nanotubes, for example, they all have to have the same orientation. However, here, you can have different orientations for different configurations, for example, and you can have a property that is independent of the orientation of your unit, your cell, for example. So the computation of stress, here I show the equation of how it's computed on lumps, and you can see that it involves the forces of the atoms, the position, the velocity, and the mass. On lamps, for example, it takes the form of the unit of pressure times volume. So it takes in consideration the entire simulation box. However, in some cases, that is not what we want, because we are valuing, for example, that example right there, a 1D material. So how can we use what is given to us by the package to compute properties only of 1D materials or 2D materials that don't occupy the entirety of the box? And the answer is that we have to do a post-processing scheme in order to readjust the stress to what we are studying. So, and this brings another question, is that, for example, we have to know the volume of the structures we are calculating. But how do we define the volume for atom-level structures, such as 1D structures and 2D structures? And there are several answers to this. First, you can use experimental reference. So, take, for example, graphene. Graphene, when you synthesize graphene, you can have graphene of many layers. If you take, for example, graphene and the graphene, for example, you have a spacing between the layers of approximately 3.4 angstrom. That means that effectively, the volume that graphene occupies, it's its area times 3.4 angstrom. So this is an example of what would be an experimental reference. However, in some cases, you don't have an experimental reference because you're, for example, proposing a new material or using something that hasn't been synthesized and you don't know. So you can use a theoretical definition. For example, this is the definition I used to estimate the mechanical properties of the carbon nanothreads. So you take basically the volume, the average volume of one carbon sp3 atom, and you times it with the number of carbon sp3 atoms. So you have the volume of your system, and you can use the length, for example, of the nanothread to estimate a cross-section area. And so you can estimate the volume. So the basic definition here is that, however, this definition is not the only one you can use. You can use different definitions. The question is that the different criteria can lead to different results, but it's essential that when you write a paper or you publish a work, that you describe what was your criteria and deploy it with consistency. So you don't change criteria when comparing different structures. That is the most important part. And also the option of using what is called 1D stress and 2D stress. These are used so you don't have to guess what is the volume of your structure. In this case, you can compare different one-dimensional structures by their 1-2D stress or two-dimensional structures by their 2D stress. So one-dimensional stress is basically given in the units of force. So basically, when you have the 1D rupture stress, is basically the force you need to apply on a one-dimensional material in order to rupture it. And analogously, we can have the 2D stress, which is force over length. So you have a force necessary to break a nanosheet of, for example, 1 nanometer, for example. So it's very comparable to other 1D and 2D structures. It's frequently available in papers and different works, and doesn't rely on this volume approximation. So what are the mechanical properties we want to evaluate on different systems? So basically, we want to evaluate the properties of rupture, so rupture stress, rupture strain. Here we can see this is a typical stress strain curve of a carbon nanotube, which we saw on the animation before. And we can see here that this is a very different curve than what most of you may have seen in the material science courses. So you have here a brittle behavior that is similar to ceramics, for example. However, you don't have a linear behavior all the way through. So this is a behavior very characteristic to carbon nanostructures, and it's very different from what you may find in your average textbook. So beyond those properties in rupture, we also can estimate other things, such as the Young modulus, which is basically the slope of the linear region of your stress strain curve, and the Poisson ratio, which basically tells you how much your structure shrinks in one dimension when you pull it on the other dimension. So this is in average something you can extract from your configurations, your trajectory. So, but also when you want to compare different materials, so specifically ones with different porosity, there are some other properties that we can use that can give you a better understanding of the mechanical behavior of your system. So for example, we have these two properties that are called specific strength and specific stiffness that relate the rupture stress with the density of your material. So normally when you compare a material that is not porous with one that is porous, the porous material is much weaker. But when you compare their specific strengths, you can see if the different materials are, for example, the porous material is being more weakened than normal by the fact that it's porous. So this allows us to make a more fair comparison between these two. In this case, the specific strength is the rupture stress over density, and stiffness is the Young modulus over density. So in this case, this property, for example, these properties are much more useful to compare different carbon nanostructures, because you can see, for example, if a carbon nanostructure is very weak, it generally tends to be one order of greatness lower than the others, for example. Besides that, I also want to point out that the accuracy of the mechanical properties we obtain, this curve, depends on the simulation parameters. And that includes the time step, the strain rate, temperature control, pressure control, and most of all, the interatomic potential. And this is something we're going to talk a little bit more over the lamps and zone today, about how this can affect the quality of the results, as you all seen in Professor Andre's talk yesterday. So also, besides the properties, we can also analyze qualitatively what happens during stress strain. And this is basically a quick video that shows how the stress in the material is distributed along the different atoms. So this is a very standard case, but today on the hands-on, we're going to see some different examples where this analysis can help you better understand your system. So this is basically what I had to say today. Thank you very much for the attention, and I'm open to questions and discussions for the time I have left.